Hi there, grade 12s, and welcome to our lesson today on calculus revision. Today we're going to be looking at all the different aspects of calculus that you need to know for your exams, and hopefully helping you just figure out a few of the problem areas that you might be having with the section. Right, so let's have a look. We're going to start off our lesson today just having a look at a checklist really in terms of what you need to know. Make sure that once you've studied your section, once you've actually spent time on this, that you can come back to this checklist and you can say, right, I know how to do each one of these sections, and basically you will then know that you are prepared for your calculus section in your exams. Having a look at our checklist, one of the first things that we need to make sure that we can cope with regards to our calculus is if they ever ask you for the average gradient of a curve, okay? Now, remember, we've learned now that when we work with our differential calculus, the derivative refers to the gradient of your tangent, or another way we could phrase that is we're working out the rate of change at one specific point, okay? Now, your average gradient, if you're ever having to calculate your average gradient, what we are looking for is the gradient between two separate points on your curve, okay? So the difference between your average gradient and your derivative, average gradient, we are working between two separate points. Our derivative, we're looking for the gradient at one specific point, okay? The formulas that we need to have, just remember when we're working with average gradients, is our f of x plus h minus f of x over h. Just to quickly remind you, grade 12, as to where that comes from, let's give ourselves a quick diagram. All right. If I had a straight line graph going through here, and I had 2 points, I have, let's give ourselves a value of x over here, and let's give ourselves a value of x plus h over there. All right. If this is x at this point, this value, the y value that's attached to our x is f of x, and the y value attached to f of x plus h, f of x plus h. Okay, so essentially to work out the average gradient between the two separate points, we are essentially taking our formula for gradient, and our formula for gradient being y1 minus y2 over x1 minus x2. Now if I were to translate that into the points that I've got on my diagram, y1 we're going to say is f of x plus h, minus y2, which is just f of x, over x1, which is x plus h, minus x2, which is h. And what you'll see is that, in fact, the h's cancel out. No, not the h's, sorry, the x's cancel out. And we're left with this formula. We're left with the formula that looks like this one over here. All right, f of x plus h minus f of x all over h is your average gradient. Okay, essentially the change in y over the change in x. Derivative, we're using exactly the same concept, all right, except what we're saying is that this distance from h, the gap between the two values for x, moves infinitely closer to 0, okay? And as the distance from h moves infinitely close to 0, so the 2 points on your graph move infinitely close to each other, all right? And as a result, they now become that 1 point that we're looking for on your graph. So therefore, we state that as our limit, as h tends towards naught, the change in y over the change in x, which we've now established is this formula, f of x plus h minus f of x all over h, is going to give us our derivative, okay? So in terms of the formulas, grade 12s, the fundamental difference between your average gradient and your derivative, your average gradient is just your change in y over change in x. The derivative, we have to state that there's a limit where the h is tending towards 0, implying that your point A and point B have now become 1 point, and we're working out the gradient at one specific point. Okay. Right, it's always really important, grade 12s, to remember that definition of a derivative, because when you remember what it is, when you have to apply your knowledge, it's always important that we can actually go back to that. So always just remind yourself that when you're working with a derivative, we're calculating the rate of change, we're calculating the gradient at 1 point. Okay. Right, so first principles is then one of the methods that we have to learn, and we're going to have a look at an example of that just now. Always make sure you know your first principles, grade 12s. It's marks that most certainly can be found in your exam. You will definitely get one of those coming up in your upcoming exams. Right, but obviously we know that we don't always have to find the derivative by first principles. We have our laws of differentiation, okay? Rules of differentiation, I'm sure we remember them from class, from our lessons in calculus. But basically, just to remind you, first of all, if I have a constant term, all right, so if I had an example like this where f of x is equal to just k, all right, a constant term, remember, will fall away. So the derivative in that case would be just equal to 0, okay? If we've got f of x, which is equal to x to the power of n, remember our law of differentiation. The n, the exponent, multiplies by the coefficient, the value in front of your x, okay? So therefore, this n over here, if you can see I've highlighted it there, gets multiplied by the x, and then we always have to subtract 1 from our exponent. Okay, so let me give you an actual example. Sometimes it's easier to see with numbers. So let's say I've got an example of 3x to the 4, all right? And we said to find the derivative of that. We're going to take 4 and we multiply it by our 3. So our derivative, there's my notation, is equal to 4 times 3, which is 12, x, and then remember you subtract 1 from your exponent, and we would get 12x cubed, which is exactly the answer that you would get if we had actually used that long method of first principles. It's obviously just that your rule of differentiation is much quicker, all right? We only use first principles when we ask to, okay? All right, and then just remember if you have anything like a constant, so let's just add a value on here. So let's say I've got f of x equals 3x to the 4, and let's add a 2 onto the end, okay? In fact, let's make it a little bit interesting. Make it 2x, and then we'll add a 2 onto the end, all right? Finding our derivative, we would state that our f prime of x is equal to, so my 4 multiplies by 3, we get 12, x to the, we subtract 1, so x to the 3. The exponent sitting above the x at the moment is just a little 1. So 1 multiplied by 2 becomes 2. And I subtract 1 from 1, which leaves me with x to the power of 0. Anything to the power of 0 is 1. So therefore, x to the 1, x which has now become 1, and anything times by 1 essentially is just itself. And then we've got this whole number at the end there, and as we said from the very first rule over here, a constant term will fall away when we use our rules of differentiation. So an example such as that would become just f prime of x, which is equal to 12x cubed plus 2. Okay, so again, we're going to practice ones that are a bit more complicated than that, but that's just to remind you of your rules. Something really important, grade 12s, which I want you to really remember when you're applying your rules of differentiation is this. Okay, it says here that when we apply the rules of differentiation, always ensure brackets are multiplied out. Okay, so when you're having to apply your rules, make sure that if you've got any brackets that are in your sum, whether it be FOIL or distribution, you multiply out those brackets. We want those gone. Okay, surds, in other words, your root signs, your surds are always changed to exponential form, all right? So anything, for example, if I've got x to the power of 3, changing that to exponential form, I'm finding the square root of x cubed, the way we write that in exponential form, is x to the power of 3 over 2, okay? So any surds must be taken back to exponential form. And finally, any term where there's an x, or whatever the variable is that you're differentiating in terms of, if that variable is in the denominator, remember you can't do your rule, you can't apply your rules of differentiation yet. You need to make sure that that variable comes up to the top where your numerator is. So for example, if I'm sitting with 1 over x, we can't use our rules of differentiation until we have written that as x to the power of -1. So just basic rules of exponents there, guys. Remember, you can't find your rules of or use your rules of differentiation until those x's are all up in the numerators. Okay, so those are just a few things that you must remember when we're doing our differentiation laws, because and otherwise you're going to land up with some problems. Okay. All right. Notation. All right, calculus is an important section with regards to notation. We've got to be able to recognize it. We've got to be able to, if it's been given to us in a certain form, we've got to be able to give it back as the derivative in a particular form as well, okay? So please remember, grade 12, that if your original function is given to you in the form f of x, all right, the notation that we give our derivative in is we say f prime of x, okay? And let's actually give the derivative here. If our function is 5x squared plus 3x, the derivative of that is going to be 10x plus 3, okay? And that's just applying our rules of differentiation there. If the same sum has been given to us, not stating f of x equals, but just y equals, okay? The notation that we're going to apply in terms of the derivative is now going to look like this. We're going to say dy over dx. So what we're stating there is we're finding the derivative of y in terms of x, okay? Now obviously that will differ depending on what the variables are in your sum. So for example, if I had, let's do it over here, if I had w equals z squared as a function, all right, and they wanted the derivative, the notation that we're going to use for our derivative is we're finding the derivative of w in terms of z, okay, and then in that answer would obviously become 2z to the power of 1. Okay, so there we go. Just watch out for that. You're finding the derivative of whatever the function is equal to in terms of whatever the variables are that they're using in the particular sum. All right. And finally, if I've got d of x and then we've got our square brackets of 5x squared plus 3x, the notation is stating find the derivative in terms of x of, and they've given you the function over there. So the rule, or the means of notation here is we have to continue keeping the d of x, all right, whilst we're simplifying the sum until the point that we're ready to actually give the derivative, all right? And when we're ready to give the derivative, all we state is just equals, okay? So if I had an example such as this, let's just give you another one. If I had d of x equals 1 over x plus, let's say, 2x. Okay? I'm not ready to find the derivative yet, and the reason why is because of this over here. This is a problem because I've got an x in the denominator. Okay? So we have to sort that out first before we can apply our rules of differentiation. So until I'm ready to find the derivative, we have to continue writing our notation, the derivative in terms of x. I'm going to bring my x up to the numerator. So remember, it becomes x to the negative 1. This 2x is going to stay as is because, in fact, it's actually fine. Okay? And now that I've done that, now we're ready to give the rule, and we're ready to apply the rule of differentiation and actually give the derivative. So therefore, in that case, we state just equals, and we apply the rule. So it would become negative 1 x to the negative 2 plus 2. And then I would finish it off. I'm not actually going to, let me do it on the side over here. I would finish it off by making it negative 1 over x squared, just to make that negative exponent positive, plus 2. Okay, so those are your notations. Don't lose silly marks on those, guys. Make sure you know your notation and that you'd actually get that all perfect. All right. The next part of your calculus section, sketching your cubic graphs. Okay, now this is quite a detailed section. A lot to remember here. We've got our cubic function, which is in the standard form of ax cubed plus bx squared plus cx plus d. Okay, and what the function of your cubic graph will always look like is that you're going to have a positive function, which will take the shape of something like that. Or you might have a negative cubic graph, which will take the shape of this. Okay? So the typical features of a cubic function is that it's got 2 turning points. Okay? If it's a positive a value, it's going to start by increasing. If it's a negative a value, the graph would start by decreasing. Okay? Remember that when we're working with a cubic graph, your turning points, all right, we refer to as our stationary points. The reason why stationary points is because if I were to draw a tangent to the curve at each of those turning points, the gradient of that tangent is flat. So in other words, there is no rate of change. It's stationary. Stationary meaning it's still, okay? So how do we then interpret that in terms of an actual calculation? If the derivative, so if it's stationary at that point, we can then state that the derivative is equal to 0, okay? And I'm sure you will remember how we do that, and that's then calculating your stationary point. Once you've got the x value, you would sub it back into the original equation and get the coordinate of your y value, okay? In terms of finding the equation of a cubic function, all right, please watch out that if you've been given a graph, grade 12s, and you look at it carefully and you can see that you've been given the x-intercepts of that cubic graph, which is quite a typical example to have, all right? This is what we need to remember over here, all right? If we've got a cubic graph and we already know, or it's been given to us what the 3 x-intercepts are, we need to start with this formula of y is equal to a x minus x1, x1 being the first x-intercept, multiplied by x minus x2, obviously being the second x-intercept, and x minus x3 being the third. Okay, so just remember that that's actually the way in which you would start putting the equation together if it was a case that you had been given the x-intercepts. If it's a case that you've been given a graph and you actually have been given the turning points, okay, then the way we're going to start putting the equation together is we have to start with the concept that a turning point is the derivative equal to naught. So that would be your starting point if it was the turning points that we had as given information, and if it's the x-intercepts as given information, that formula of a x minus x1 multiplied by x minus x2 times by x minus x3 is the formula you're going to use for that. All right. These are all just things you have to keep up your sleeve and just remember them so that in your exam you can apply that and it actually makes it quite easy. All right, guys, and then generally speaking, the last part of your calculus section is your maxima and minima, all right, where you have to calculate the maximum area or the minimum volume of all sorts of different scenarios, okay? It doesn't always have to apply to surface area and to volume. It could apply to very multitude of different scenarios, but typically speaking, volume and surface area are pretty common. So you need to know your volume and your surface area formulas well, okay? Unfortunately, you don't get them in any kind of formula sheets, so you do need to make sure that you know how to calculate. And this goes back to grade 9 and grade 10 and grade 11, how we worked out the volume and the surface area of all sorts of different prisms, okay? Once we have calculated these formulas, okay, to work out the maximum and the minimum volume or surface area or whatever the question requires of us, we go back to the understanding of a graph, okay? When we had our cubic graph, to work out the maximum or the minimum turning points, we always went with the concept of letting the derivative equal 0, okay? So if I've got a formula that represents the volume of a particular prism, all right, and I want to know a value for x that will maximize the volume of that prism, we take the derivative of the formula and we let it equal 0, okay, based on the concept that that would give us, if we were to plot it as a graph, it would give us the maximum value on that graph, okay? So derivative equals 0 is going to be what we use to then help us calculate that maximum or minimum, all right? And lastly, all right, lastly with regards to functions, and this is quite tricky, guys, so please make sure that you practice this. When we have a cubic function, sometimes what they're going to do is actually give you the graph of the derivative function, okay? Now we need to think about this. If a cubic function started with x cubed, all right, then a derivative would then go one degree down and it would become x squared, okay? So the derivative of a cubic graph is actually going to be a quadratic function, okay? And we need to be able to interpret that and to understand how I would go from a derivative function to a cubic function, okay? And we're actually going to do an example shortly just to explain how that works, okay? All right, guys, so there's a lot of theory that needs to be learned, just like many sections in maths, but if you know the theory, it makes the application just so much easier. So please make sure that you are very familiar with all of that. Right, let's quickly start with one of the most common beginning questions in terms of calculus, and that's your first principles. Okay, so A is asking us to determine f prime of x, which remember is your derivative, from first principles. Right, so we're going to take the formula f prime of x, which is equal to our limit, where h is tending towards 0, and we've got our f of x plus h minus f of x all over h. All right, and we've already discussed where that formula comes from and where it actually was derived from. So using this formula now, we are going to get our derivative. Please make sure that you write your limit, h tending towards naught, all the way down through the steps of your sum. It's only when we actually put that limit into our equation that we don't write limit anymore, okay? Right, so f of x plus h. Remember, this is your f of x over here, okay? So if f of x has x's over there and x's over there, then if I'm working with f of x plus h, it's going to imply that I'm going to take exactly the same sum, except where I've got an x, I have to replace it with x plus h. So therefore, we've got the following. I'm going to have negative 3. Instead of x, we've got x plus h squared. And instead of x, again, I'm replacing that with x plus h. So that's what f of x plus h is as a function, okay? So f of x plus h is negative 3 x plus h squared plus, so I'm getting x plus h. All right, so I'm just getting that from over there. Minus f of x. F of x is this equation over here. So it's the original f of x equation of negative 3x squared plus x all over h. Okay, now it's a case of tidying things up. We're going to have to multiply out, h tending towards 0, and I have got negative 3. We've got x squared 2xh plus h squared. We just FOILed that out. I've got x plus h, and minus, then two negatives are going to make positive, 3x squared minus x all over our h. Distributing our 3, can you see I'm writing limit every single time? Distribute your negative 3, so we've got negative 3x squared minus 6xh minus 3h squared plus x plus h, 3x squared, and x all over h. Okay, quite a nice checkpoint at this point, grade 12s, is that if you ever have any values that don't have an h in it, they must cancel. Okay, so it's quite a nice point at the sort of stopping point at this stage and saying, okay, let me just check that I'm on the right track. So I've got a value of negative 3x squared, and that's going to cancel out with the positive 3x squared. So those are gone. I've got a positive x and I've got a negative x. Those are going to cancel out. Let's just check here. This term has got an h in it, so I'm happy. That term's got an h in it, so I'm happy, and that's got an h, so I'm happy. So therefore, all the terms have to have an h in it. Why is that the case? Because remember, with your limits, what's going to happen now is that the limits of h tending towards naught needs to be substituted into your sum. But if I were to substitute naught into it as it is at the moment, that would make the denominator 0, and it would make it undefined. And we don't want that. So what we're going to do is we are going to take out h as a common factor from your numerator, giving us negative 6x minus 3h plus, and if I take h out from that term, I'm left with just 1, and it's over h. And that's going to allow us to cancel the problematic h that's in the denominator there, okay? And with putting that naught into your function, we're now going to have negative 6x minus 3, and the h has now become naught plus 1, and that gives us negative 6x plus 1, and that's our derivative, okay? And what's great about this is that, in fact, we can quickly apply our quick rule of differentiation. Let's check if we're right. If I were to multiply the 2 into the front, we would get negative 6x, and that would become plus 1. Is that the same as what we got over there? Yes, it is. Okay, so there's our derivative, guys, and we obviously you will always get one of those in terms of first principles, so do make sure that you know how to do that. Very quickly, what we're going to have a look at as a second part of that question is just quickly looking at the concept of a function and its derivative function, all right? Let's say the question said to us, sketch your f. So we're taking the example that we've just done in the previous question in terms of finding the derivative, but this time we want to sketch the graph as well as its derivative on the same set of axes, okay? So let's quickly do this. We're going to set ourselves up an x and a y axis, okay? And we are going to sketch let's sketch the derivative. Remember that your derivative was negative 6x plus 1. Okay, so that's linear. That's a straight line graph, all right? If I were to sketch that, I've got a y-intercept at 1. The x-intercept is going to work out to be 1/6, so it's very, very small. It's right over there. Let's make positive 1 over here. Let's make negative 1 over there, all right? So if I were to sketch this graph, it's going to, let's give ourselves a green line to do it. It's going to be a straight line passing all the way down through there, all right? Now, what's the relationship between that derivative and the original function of f of x, okay? The original function of f of x is a parabola. If I were to sketch that parabola over there, let's quickly see. I can work out that it's got a y-intercept of 0 because there's a naught at the end over here. And the x-intercepts, if I take out an x as a common factor, I'm going to have negative 3x plus 1. That's equal to naught. So I would have two values for x. X is equal to naught and x is equal to a third. Okay, so that would be a naught and a third. Let's put, that's going to have to be around about there. Okay, and we know that it's a frowning function. We know that it's a negative parabola because it's a negative 3. So therefore, and we're going to give ourselves a line. Let's just put a line through here. As an axis of symmetry, it's going to look something like so. Okay, so this is just a sketch. We're not getting too detailed with our sketch itself. But what I want to point out to you guys is just the relationship between the two graphs, okay? Look at your straight line graph. That represents the derivative. Where the derivative was equal to naught, okay? So where the derivative is equal to naught. If we look at the straight line graph, that would imply the x-intercept over there, all right? Now, the x-intercept of your derivative correlates to the turning point of your f of x function, all right? So remember, and we know that. Remember, we knew that the derivative equals to naught was the turning point of your cubic function. So therefore, if you ever have the picture of a derivative and you know where the derivative is equal to naught, that would translate back to being the turning point of your cubic function, all right? The other thing we know is that because this is a negative gradient in terms of my straight line graph, a negative straight line graph will imply that I'm going to have a negative parabola. So therefore, we know that it's a frowning shaped parabola and not a smiling shaped, okay? And the other thing we know is that the second derivative, okay, now the second derivative would be over here. If I found the second derivative, which is going to land up just being negative 6, the x would disappear, and we have to let it equal naught. Okay, so the second derivative equals naught, which actually lands up being this point over here. The second derivative is always the y-intercept of your original function. Okay, so these are things that you just need to make sure you understand clearly with your derivative function, is that where the x-intercept is, that will then translate to the turning point. Look at the shape of your derivative function. If it's a negatively shaped graph, it's going to imply a negatively shaped function, a cubic function. And the second derivative equals 0 means that would actually give you the y-intercept of your original function. Okay, so as I say, you do need to go practice those. They do take a bit of practice, but as long as you understand those concepts, then you should be fine. All right, guys, we're going to take a short break. We've gone through a lot of theory, so take a moment to think about it all, and we'll be back shortly. Hi guys, and welcome back. Right, we're going to carry on having a look at your calculus. We've already had a close look at doing first principles, and we've had a look at a derivative function as well as the original f of x function. Those are important concepts that you need to go and practice. Now let's move on to your rules of differentiation. Okay, we have already spoken about it briefly, but we need to look at an example that involves a little bit more technical working out, okay? So let's have a look at this example over here. They've asked us to find dy over dx if, now notice the notation, we spoke about this earlier, if y is equal to, and they've given us a whole sum with all the variables being x, okay? So we're finding the derivative of y in terms of x, okay? So just the notation being that. Okay, so we're going to go ahead and do that. But we cannot just dive straight into finding the derivative because there's actually stuff that needs to be done here. I've got a problem with that denominator over there. And that is that we can't use the rules of differentiation until all our denominators with a variable in it have come up to the numerator. The other problem is that I've got a surd. Okay, so we've noticed that I can't have a surd and I cannot have a denominator with x. So let's sort those problems out. While I'm sorting those problems out, I have to keep my notation as y equals because I am not finding the derivative yet. 8x cubed is going to stay as is. I'm now going to write this as 4x to the half. And let's look at it like this. These two separate terms, 4x squared and 3, are both over this one denominator of x. Make your life easier and separate it. Split them up and give them each their own denominator of x. Okay? Because by doing that, you can actually see that it's much easier to simplify. So I've got 8x cubed. My 4x to the half is going to stay as is for now. And, okay, so this x will cancel with one of the x's in the numerator. So I'm left with just 4x. And instead of having 3 over x, let's write it as 3x to the negative 1. Okay, so now what we've done is we've solved those two problems. So now we can go ahead and actually work out the derivative in terms of x. Okay, so dy over dx equals, and now we apply our laws of differentiation. 3 times 8 is going to give us 24, and that's x squared. 4 times by a half, that's going to leave us with negative 2. X to the, if I subtract 1 from a half, we're left with negative a half. If I multiply 4 by 1, we have just 4. And remember, if we subtract 1 from 1, we're left with x to the naught, which is actually just 1. So therefore, it's just 4 times 1, which is 4. And negative 3 times, well, 3 times negative 1 is negative 3. So let's just correct that. Negative 3. And it's x to the negative 2. Okay, so lastly now we just simplify, we tidy up, we make it look better. So we've got 24x squared minus 2 over. I don't want to leave that as a negative exponent, so I'm going to bring it down to the denominator. And I'm actually not going to leave it in exponential form. I'm going to put it back into surd form. X to the half, putting it back in surd form, is just x, the square root of x. Okay? This 4 is going to stay as it is, and 3 over x, because I'm just making this now back to positive, so I bring it to the x squared down to the bottom, and it returns back to being a positive exponent. All right, and there we go, and that's your derivative. So a little bit more complicated. You can see how I changed the surds back to exponents. You can see how I didn't leave the x in the denominator. I had to bring it up to the numerator, and only once you had actually found the derivative, then you can bring the variables for x back down into the denominator. Okay. All right, guys, so I hope you understand that. And again, go and practice those. Okay, now we're going to look at another very common question that comes up in your papers. The question's basically said to us, the gradient of the curve y equals negative 3 over 2x squared plus 7x minus 4 at a certain point is 1. Find the point. Okay, so we need to interpret what they're saying to us over here. They've said the gradient of the curve of that equation at a certain point. Okay, now we know it's been drummed into us that the derivative is the gradient at a point. Okay, so if we know that, then the gradient of the curve of this equation at a point is 1. So does that imply then that the derivative of my function, my dy over dx, has got to be equal to 1. All right, do you understand why? Because the derivative at a point, so therefore what I've done is I need to work out the derivative of my function. And we know that at that point, the gradient is equal to 1. So I've made the whole thing equal to 1. All right. As long as we understand that, guys, the rest of the working out is easy, okay? But as I said to you earlier, it's so crucial that you remember what the derivative actually is, okay? We tend to use the word so often that we tend to lose focus on what it actually is. If you remember that your derivative is the gradient of a curve at a point, then it makes the interpretation of a question like this quite straightforward. Okay, so let's work out our derivative. dy over dx is going to be equal to, do you notice here that I don't have any problems? I don't have any x's in my denominators. I don't have any surds. Everything is fine to go ahead and to work out my derivative. If I multiply 2 by negative 3 over 2, the 2's will cancel and I'll be left with negative 3x. My x is going to multiply by 7, or 1 multiplied by 7, which leaves me with just 7, and the constant term of 4 is going to fall away. And we are then going to make our negative 3x plus 7 equal to 1. All right? That's going to leave us with negative 3x, which is equal to, if I move 7 over my equals, it'll become negative 7 plus 1, which is negative 6. And dividing by negative 3, we get ourselves an x value of 2. Okay? Now, the question did ask, find the points. Okay? And a point is always going to be made up of an x and a y coordinate. So we've got the x value, but we still need the y value. Okay? Where do we substitute the y value? Where do we substitute the x value to find the y? Do we sub it back into the original function, or do you sub it back into the derivative? If you think about it, I hope what you're telling me is that you sub it back into the original function. Okay? Once you've got the value for x, to find the corresponding value for y, always back into your original function. So therefore, we are going to substitute 2 into all the x values of our of our original function of y. Okay, 2 minus 4. And what's that going to give us? So that's going to give us 4 negative 3 over 2 multiplied by 4 plus 14 minus 4. 2 will go into 4 twice, so that gives us negative 6. Negative 6, and that's going to give us 10, and that obviously leaves us with 4. Okay, so therefore, what is the point that we are looking at? It is the point of 2 and 4, all right? And just to clarify for you that that point of 2 and 4 is actually the points of contact between your the quadratic function that we've got in this example and its tangent. Okay, so that's what we've worked out, and we've worked out that we were given that the gradient of your tangent was 1, and the point of contact we've now established is 2 and 4. Okay. All right, guys, so remember, derivative is the gradient at a point. So if you remember that, you will manage these questions without a problem. Our cubic graphs, okay, these are always worth a fair bit of marks in your exams, so just make sure that you know how to sketch them, make sure how to interpret them. Lots of marks to be found in these questions, okay. This particular example, we're not asking you to sketch the graph, but what we're asking you to do is a whole lot of interpretation, okay? So let's take a careful look. When they've given you a graph like this and you have to interpret it, take a moment to just really carefully read the given information, because obviously everything that's been given to you is there for a reason. So we know that the above sketch represents the function f of x, which is equal to our x plus 3 squared, multiplied by a negative x plus t. We've been given that point A is a third and the coordinate of A, which we don't know, and C, which is negative 3 and 0. Okay, so let's just take a moment to assess what we've got over here. I've got a formula I've got a cubic equation, but it's not complete. I don't know this value of t that we're obviously going to have to work out. I've been given the 2 x-intercepts, all right? And I'd like to point out something quite interesting to you just in terms of the equation. Do you notice that this x-intercept over here is actually bouncing off the x-axis? All right, it's not actually, it doubles up as an x-intercept and a turning point. In an equation, whenever that happens, that bracket will have to be squared, okay? So if you didn't know that already, please take note of that a point that doubles up as an x-intercept and a turning point will always be in your equation a bracket squared, okay? So the other point is then our negative x plus t, and this first question is asking us to prove that t is equal to 2. All right, so let's see how we can go about doing that. I know that I have turning points, and I know that if I've got turning points, somewhere along the line that's got to imply that I need to make my derivative equal to 0. Okay, so based on that, so I'm going to have to now manipulate this equation to a point where I can find its derivative and I can hopefully let it equal to naught. Okay, so that's the path that we need to head on. So let's simplify this equation out. Let's just make it look a little bit more in terms of how we would know it to be. So the first thing we're going to have to do is square this bracket out. So it's going to be x squared. I'm going to have 6x, and I'm going to have 9. And I've got negative x plus t. All right. This is just a bit of distribution. This negative x is going to have to multiply to all 3 terms in the first bracket. And then it's going to have to multiply with the t by all 3 terms as well. So this is what we're going to be doing. Okay. So nothing other than just careful working out here, guys. Negative x cubed minus 6x squared minus 9x. That's the first set of distribution. Then I've got plus tx squared. I've got plus 6xt. And I have got 9t. So I've multiplied this all out over here. All right. What I'm going to do now, guys, is I'm going to simplify this a little bit. If you look at this carefully, you'll notice this. I've got an x squared term here, and I've got an x squared term here. So those are like terms. All right. So this is what I'm going to do. I've got x cubed, and I don't have any other x cubed terms, so that's going to be on its own. These two terms that have both got x squared in it, I'm going to take an x squared out as a common factor. And I'm going to group the negative 6 and the t together as the coefficient of your x squared term. Okay. Then I've got an x over here, and I've got another x over here, and I'm going to do the same thing. I'm going to take out an x, and I'm going to group together the negative 9 and the 6t as the coefficient of your x term. And then lastly, this 9t over here, it doesn't have an x in it. So essentially, it's a constant. Okay, we're finding the derivative in terms of x, and that term didn't have an x in it. So therefore, we take it as a constant. Right, so now we're going to find the derivative of this. So the derivative of this is going to be negative 3x squared. That one's easy to see. I'm going to multiply 2 in front, so I'm going to have 2x. Remember, you subtract 1 from your x, and I've still got negative 6 plus t being multiplied to that term. I've got, remember, if you're finding the derivative of just an x, the x will fall away. If I do it, multiply the 1 in front, and the x falls away, and we're still left with negative 9 plus 6t plus 9t. Let me clarify, when I say falls away, let me just make sure I'm not confusing anybody. Remember, when you multiply 1 in front, you get your 1, and we subtract 1 from our exponent. So 1 minus 1 gives you naught, and anything to the power of naught is 1. So 1 times 1 got you the 1 that's sitting over there. So when I say x falls away, that's where it went to. Okay. All right, so now that we've got the derivative, let's make our derivative equal to naught, because that's what we do when we have a turning point. Okay, and let's actually save ourselves a bit of working out time over here. Let's now look at the 2 turning points. I've got turning points and I've got x coordinates. So let's take an x coordinate at a turning point. Let's take a third, and let's substitute it into the x's. Okay. Plus 1, I've got negative 9 plus 6t, and sorry, I need to correct myself here. What have I done? That was a constant term. And the constant term, when we find the derivative, falls away. Okay, so let's just make sure we are correct there. So we've got 3x squared plus 2x, and everywhere we've got x, we've replaced it with a third. Okay, negative 3. That gives us 1 over 9. This is going to give me 2 over 3. I've got negative 6 plus t. And I've got negative 9 plus 6t. Okay, so let's now simplify. I've got naught, which is equal to, as a fraction, that's negative 3 over 1. So 3 will go into 9 3 times. So I've got 1 over 3. As a fraction, that's 6 over 1, so therefore 3 will cancel with 6 twice, and we're left with negative 4. Okay, so we've got a negative 4. and I've got a 2 over 3t, I've got a negative 9, and I have got a 6t, okay? The best thing to do in a situation like this is balance everything out as a fraction. Put everything over 1, all right, and find an LCD. LCD I'm going to find is 3, so therefore I'm going to multiply by 3, by 3, and by 3, and the golden rule of fractions, what we do to the bottom, we have to do to the top. So leaving us with negative 1 minus 12 plus, okay, that's a 2t. 9 times 3 is going to be 27, and 6 times 3 is 18. And let's add up. And what you'll notice here is that I've dropped my denominator, because when we find an LCD on either side of an equal sign, the LCD can fall away. Right, negative 13 minus 27. Let's just make sure we add this up nicely. Okay, so we've got negative 1. We've got minus 12, which is obviously minus 13. I've got minus 27. Those are my constants. So that's negative 40. Okay, and then I've got 20t. Right, and when I move 40 over, we can say that 40 is equal to 20t. And when I divide 40 by 20, we get 2. Okay. And that's what they asked me to prove. All right, so it's a bit of a calculation involved there, but based on the theory, I knew that I had turning points. I knew that I had to find the derivative, and I had to let it equal to naught. And I had values of x that I needed to get rid of. Okay, I was trying to solve for t. So I substituted one of my x coordinates of my turning point into the x's, and you were left with t to solve. All right, so there we go. So now we've got the value of t. We know that it's 2. So the next question is now asking us to find the coordinates of B. All right, look at your graph. What can we say about point B? It's an x-intercept. Okay, together with this one over here. Remember, this was also an x-intercept as well as a turning point. So we've just worked out that our function is f of x is equal to, I've got x plus 3 squared minus x, and don't forget we've just proven that t is the value of 2, okay? So they want us to work out the x-intercepts. Now, to work out an x-intercept, we need to say, let y equal 0, all right? Don't go and multiply this all out, because if you do, you're going to have to just factorize it again, and you're going to get back to exactly what you're sitting with over here. So if you're trying to work out an x-intercept, and your brackets are already factorized on the right-hand side, please don't multiply them out. That the work has already been done for you. So naught is equal to, if I let the brackets of x plus 3 squared equal 0, or let the bracket of negative x plus 2 equal 0, those are going to give me my two x-intercepts. The first x-intercept being negative 3, and the second x-intercept being 2. I already knew that that one was negative 3, so therefore B is going to be 2, all right? And just obviously make sure that you answer the question asked. They're asking for the coordinates of point B, so therefore point B is the coordinates of 2 and naught, okay? All right, so always make sure you go back to your question. Make sure you are actually answering what it is that they are asking. Now that we've done that, they're asking us to calculate the value of a. Now remember, we know this point over here, the x-coordinate is a third, but we don't know what the y-coordinate is, okay? And they're asking us to find that. So once again, let's go back to our formula. We've established that we have an f of x, which is equal to x plus 3. It's all being squared. And I had a negative x, and we know that t was 2, all right? This is a turning point, okay, but apart from being a turning point, it's also just another point on your curve, okay? So remember, and this doesn't only apply to a cubic function, it applies to any function. If you've got an equation that represents your curve and you've got an x coordinate, you can always find the y coordinate, or vice versa, by substituting that point into your equation. So that's exactly what I'm going to do. I'm going to work out what f of a third actually is. So I'm going to substitute a third into each of my x's, and I'm going to do the working out, and I'm going to quickly work it out over here. So we're going to have our bracket, and I have got a third, which is plus 3, and the whole bracket is being squared. Sorry, that's going to tell me I've got an error there. The whole thing is being squared. And I've got a negative third, and that's plus 2, and we're landing up with, okay, so they asked us to give it to 1 decimal place, so 18.5 is the value. So f of 1/3 is going to give us 18.5. So therefore our value for A is 18.5. Okay. So a question like that is really just making sure you understand the concept that if you have an x coordinate, you can always find its y coordinate, its partner, by substituting that value for x back into the equation. Okay. Welcome back. Right, let's have a quick look at an example regarding maxima and minima. All right. We're going to apply an example using volume and surface area and what have you, because those are always your most common type of questions. The length of a wire 200 meters long is cut into 2 pieces. One piece is used to form an equilateral triangle, x units in length. The other piece is used to form a square. So we have got a line, and this line has been cut into 2 pieces. All right? And one piece has been basically bent up into the shape of a triangle, and the other piece has been bent into the shape of a square. Now the total length of your piece of wire was 200 meters. And they've said that it breaks it up into equilateral triangle of x units in length. So therefore your equilateral triangle is sitting with an x on either side of each length, okay? So that means that the piece that got bent into your triangle is going to be a length of 3x units, and what was left for your square would be 200 minus 3x units. Okay, so it says that show the length of the sides of your square are given, and they actually tell you the answer that we're looking for. We want to prove that the length of your square, each length of your square is 50 minus 3 over 4x. Okay, so let's take the 200 minus 3x, which is going to represent the perimeter of the 4 sides of your square. All right. If each side of your square is equal in length, then to work out one side of our square, I would have to divide by 4. 200 divided by 4 is 50, and 3 over 4x is what is left, and that's one side of your square, which is exactly what they asked me to prove. Okay. Now that we've done that, they're wanting us to determine the area of the square in terms of x. Now, the area of a square is length times breadth. So if we've just worked out that one length of our square is 50 minus 3 over 4x, the length times breadth would have to be the bracket squared. All right, so 50 times 50 is going to be 2,500. I've got 50 times 3, which is, I'm going to have to work that out over here. Let's just make sure we do it. So 50 multiplied by your 3 over 4. Okay, 75 over 2, and I'm going to double that because we've got an inner and an outer, so therefore we're going to land up with negative 75x and plus 9x squared over 16 when I square the last 2 terms. All right? So determine the area of the square in terms of x. That's what we've got for our area. Okay? So now that we've done that, the next question is going to be the one that always involves the maximum and minimum. We now need to determine the value of x so that the area of your square is going to be a maximum. So taking this area formula that we now have, to work out the maximum, as we spoke about earlier, we work out the derivative of your area in terms of x, and we let it equal 0. And by doing that, you're going to find your value for x that is going to give you your maximum. So the derivative of your area formula in terms of x, 2,500 doesn't have a value for x, so therefore it falls away. Negative 75, 2 multiplies, so therefore I'm going to land up with 9x over 8. That's the derivative, and we're going to let it equal 0, so negative 75 plus 9x over 8. And let's just make that positive 75 equals 9x over 8. 75 times by 8. 75 times by 8. That's giving us 600. 600 equals 9x. And we're going to divide by 9, leaving us with 66.67. 67 as a value for x. Okay, so there we go. That's what we've done. If the question went one step further and actually wanted to know what was the actual maximum area for your square, we would then just take that value for x and I would sub it back into the area formula, giving you the maximum area for x. All right, guys, so as I've said before, please make sure you are very familiar with all your area, volume, surface area formulas, because those will need to be very clear and you need to know them well in order to apply this section. And that's it. All right. So lots of practice, guys. We've covered all of those sections. If you are familiar and you've practiced well with all of those aspects of calculus, I have no doubt you will do very well in this section. It's an awesome section. It's fun. Go and enjoy it. And I'll hope to see you next time. Thanks so much. Bye.